Okay, so here let me introduce the homework problems that relate to inner product spaces and norms. Okay. All right, so in exercise 1.0, give the definition of a positive definite symmetric bilinear form. You may denote the form as A of x and y. Now really in this exercise you can summarize all of the properties of positive definite symmetric bilinear form that we showed in class. And you can consult the video that I made for this purpose. Now, in the video I used the letter B instead of the letter A. However, this is a minor change. You may just simply replace. Okay. Exercise 1.1. Using the definition of bilinearity, express A of C1x plus C2x prime with C3y plus C4y prime in terms of these separate inner products. Okay. Exercise 1.2. Given a Euclidean space Rn. Now, a Euclidean space is simply n-dimensional space. You can think about R2, which is the plane, R3, which is space. Rn is a generalization of these two spaces. R2 has two-dimensional vectors that have two components. R3 has three-dimensional vectors with three components. Rn has n-dimensional vectors with n components. All right? So given the Euclidean space and a real constant k, for any x and y in the Euclidean space, define this inner product. Well, we'll show that it is an inner product. We'll define this quantity, x and y, and I put the subscript k to indicate that this quantity depends on k. And we define that as k times the norm or length of x plus y squared minus the length of x minus y squared, where z denotes the Euclidean norm on Rn. And I want to show that this is a positive definite symmetric bilinear form if and only if k is greater than 0. So let's take a moment to look at this problem. Okay, so here let me go and start a new page. So this is inner product spaces homework. All right, so let me look at this particular problem that we're looking at and see what we can say about this. I'll make this a little bit smaller so you can see it. Okay, here we are. Okay, and let me go and see if I can make this a little bit bigger. I can make this a little bit bigger as well. Okay, all right, so remember I mentioned that this Euclidean norm, x plus y squared, is equal to, so let's see what we can do here. If I take this quantity x plus y squared, this is simply equal to x1 plus y1 squared plus x2 plus y2 squared plus dot 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 plus xn plus yn squared. So this, if you think about this, this is the Pythagorean theorem for x plus y. Okay, this is the first component of x plus y, second component of x plus y, last component. So similarly, of course, you can express x minus y squared. So I can write that down to x minus y squared is equal to x1 minus y1 squared plus dot 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 all the way up to xn minus yn squared. Now remember, these are components and not vectors. So what you want to do is take the difference and simplify. Okay, take the difference of these two and simplify. And then you want to show the result is positive definite symmetric bilinear form. So you can call the result x, y, k. Okay. So if you do this, take this difference and simplify and multiply by k. Multiply by k, and this will give you a formula. This will give you a formula for xyk. Okay, call that result xyk, and you can use this formula. Use this formula to show the properties. To show the properties. Okay. Now, what are the properties? Just to remind you what they are. You have positive definite. You have, that's going to be xy. Sorry, xx. Xx is greater than or equal to 0, and xx equals 0 only if, which I can also write implies, x equals 0. That's positive definite. Then I have symmetric. Sorry, I forgot to put the k here. So these are properties you want to show. You want to show that xyk is equal to yxk. Okay. Then you want to show bilinearity. And that one is going to be what we've seen before, c1x plus c2x prime. Sorry. And I take the inner product of that with c3y, c3y plus c3y prime. c4y prime, sorry. Is equal to, I'm sorry, well, let's do it this way. We can show in two separate ways. Okay, and here you can say y is equal to, now you know this property because we showed this before, or I can show, and I can also show x and c3y plus c4y prime is equal to this one. I'm not writing this property again because you know this property already. All right, so that's what you want to do for this problem. All right, let's move on to the next problem. Okay, that would be exercise 1.3. All right, so we've talked about inner products in the set of vectors, Euclidean vectors, like in two-dimensional space or three-dimensional space. But this idea can be generalized. Suppose we have the set of measurable square integrable functions on 0, 1. This set is denoted by L2. I do not know if you're familiar with L2, but you should just think about this as a set of functions which are square integrable. In other words, you can take the integral of the square of this function on 0 and 1, on the interval 0, 1. Okay. Right. So there's an inner product on this space, and it's defined as an integral in this way. The inner product of f and g is the integral from 0 to 1 of f of x times g of x. I want to give a formula that expresses fg in terms of the norm of f plus g and the norm of f minus g. So let me explain some other of these concepts. Okay, so let's look at this problem here. And I think we'll stop the video with this one here. Okay. All right. All right. So here we have a set of measurable square integrable functions. It's denoted this way. And we have this. Okay. All right, now, so let's try to make this formal. L2 of 0, 1 is equal to the set of functions f such that f is a function from 0, 1 to r. All right, that means that f is a real valued function on the interval 0 to 1, and the integral from 0 to 1 of f squared, I'll put an absolute value, which it's really not necessary because we have real functions. So f squared of x dx is less than infinity. All right. These are square integral functions. Okay. So they're functions on this interval, and they also the squared integral is less than infinity. Okay. So for example, okay, any continuous function is in L2. Okay. I could also take a function something like suppose I could take the function f of x is equal to, say, x to the minus 1/2. All right, now this is not a continuous function because, okay, so notice that this is not defined at 0. So maybe instead, it's not defined at one point, but I'm going to ignore that problem. That can be fixed, but let's just ignore that for now. If I take this function, I take the integral from 0 to 1 of f of x squared. Okay, looks like I'm not going to get it for this one. So instead of minus 1/2, let's try something else. Well, all right, let's look at this. We can look at this. This is fine. F of x dx, f of x squared dx. It's going to be the integral from 0 to 1 of x to the minus 1 dx. Okay. Now, if you remember what the integral of x to the minus 1 is, it's logarithm. So we have the logarithm evaluated at 0 and 1, which is 0 minus, now what's the log of 0 is negative infinity, which is equal to infinity. Okay, so f of x is not, this function is not in L2. All right, but however, we could modify this slightly, just a little bit. If I took instead of f of x equals x to the minus 1/2, I could take f of x is equal to x to the minus, let's try something like this, 499 over 1,000. Okay, let's try this. Okay, so if I take the integral from 0 to 1 of this function, now if you think about what the square of f is, when I square if I square a variable with the exponent, I'm going to double the exponent. Now the double of minus 499, if you think about it, is minus 998. Okay. Now if you remember your integration rules, when you integrate a power of x, except when the power is minus 1, the result is going to be the power plus 1 okay, it's the power plus 1, and then it's going to be divided by that same power. Okay, and I evaluate that from 0 to 1. Okay, so when x is equal to 1, I'm going to get 1 to this power, 1 minus 998 over 1,000. Okay. Now, in fact, I could rewrite that. That's the same as 2 over 1,000 if I put the both terms on common denominators. So that's 1 to the 2 over 1,000 divided by, on the bottom I also have 2 over 1,000. Okay. So that's equal to actually 1,000 over 2, which is 500. Okay. All right, so that's 1. Now if I put in 0, I get 0. So this is the result. The integral of that function is 500. So this f of x is in L2. Okay, is in L2 of 0, 1. So those are just some examples of L2. We'll be seeing L2 quite a bit in this course. L2 is a very important space in the idea of functions. It's actually called a Hilbert space. You may have heard of this idea. And this is actually a vector space. It's an infinite dimensional vector space. All right? So here we have an inner product. I didn't ask you to prove this is an inner product, but in fact it is an inner product. One thing you can see easily is symmetry, because if I replace the f and the g and exchange the f and the g, the value of this integral does not change. So it's easy to see that this one is symmetric. It's also quite easy to see a positive definite, because if I take f, inner product of f with f, I get the integral of f squared. But f squared is always non-negative, so this integral will always be greater than or equal to 0, and the only way the integral is 0 is if f is 0 everywhere. Okay. Now what I want to do is give a formula that expresses fg in terms of this norm f plus g and the norm f of x minus g. So let me just remind you what f of x plus g is. Okay. The norm of f of x plus g, so in L2, okay, the norm of some function is defined as, okay, the norm of f of L2 is defined as the integral from 0 to 1 of f squared of x dx. If that's not all, I take the square root. So I hope you can see some similarity here between this norm and the norm for our Euclidean space. When we took our Euclidean space, we took the sum of squares of components. I think I have that up here. Right? The sum of squares of components. All right? Here we're taking the sum of squares. An integral is like a sum, so we're taking a sum of squares also. And I'm taking the square root, just like we did in the Pythagorean theorem. Okay. So if we have this, we have this. So let's think about if I take the norm of f plus g is going to be equal to the integral from 0 to 1 of f plus g squared. I'm just substituting f plus g into the definition. Okay. So it's integral of f plus g squared to the 1/2. Okay. And sorry, there's a dx here. And similarly, you can have the norm of f minus g. And this is equal to the integral from 0 to 1 of f minus g squared dx, also raised to the 1/2 power. Okay, so this exercise that I'm asking you to do, which is exercise 1.3, I'm asking you to relate these two quantities. Asks to relate, to express f, the inner product f with fg in terms of f plus g and f minus g. Okay? And what I suggest you do is you simplify these expressions. Do this by simplifying the expressions for f plus g, and I'm going to say simplify the expression for f plus g squared and f minus g squared. Right. If you simplify these expressions, you may be able to see some relationship between the result and this inner product. And then, so relate the results to this inner product of fg. And remember, fg is defined as the integral from 0 to 1 of f of x times g of x dx. All right? So I'm going to stop this video here, and these are 3 exercises I would like you to work on. If you have time tonight or tomorrow morning, I would like you to work on these. All right, thank you for watching.